Assalamualaikum and good morning to Sir Syed Muayyad Syed Ali. So this is presentation for Group 1 for subject Dcc50203 Reinforced Concrete Design. Our group member consists of me, Azad bin Daziz, 07DK21F2004.
Next is me, Muhammad Fidos bin Amiran, matrix number 07DKA21F2006.
My name is Muhammad Sami Sofian bin Ronto. My matrix number is 07DKA21F2014.
My name is Nasahal Karul Izzat with number matrix 0721F2030.
My name is Muhammad Hafiz bin Abdul Muin. My matrix number 07DKA21F2012.
What is reinforced concrete? It is a composite material consisting of steel reinforcing bars embedded in a hardened concrete mixture. So, there are two behaviors of reinforced concrete. For concrete, it is high in compressive strength but weak in tensile strength. But for reinforcement, it is highly in tensile strength but weak in compressive strength. So, in this subject, we are learning on how to design slab, column, and also beam.
Next, we move on to design of slab. What is slab? A concrete slab is a common structural element of modern buildings, consisting of a flat, horizontal surface made of cast concrete, steel reinforced slab, typically between 100 and 300 mm thick, most often used to construct floors and ceiling, while thinner mud slab may be used for exterior paving. And this is the photo of slab. After that, types of slab. Slab have two types. First is one way and second is two way. One way slab is a slab that bears the load in one direction mainly. It can be a slab supported on two edges only, or a slab supported on four edges for which bigger span length Ly is at least twice the smaller span Lx. And two-way, a slab supported on all four edges with an aspect ratio of longer to shorter, theoretical span less than 2, is considered to be two-way. Static analysis of two slabs subjective to uniform load is performed using table which give the fundamental support moment, span moment, and shear force. So for one-way slab, this is the example for one-way slab where the value of Lx over Ly is more than 2, and for two-way slab, Lx over Ly is less than 2. Next, there are several types of reinforcement concrete slab. As we can see, first is one-way solid slab, next two-way solid slab, rubber slab, waffle slab, flat slab with drop panel. And this is the example of type of reinforcement concrete slab. Now we move on to how to solve the question of simply supported one-way slab, and the question is like this, as we can see. So for step how to solve it, step 1 is determine the design life, exposure class, and fire resistance. Step 2 is determine material strength. So step 1 and step 2 we combine it on one-way calculation. So first we do is specification. Effective length, effective span L 4.25 meter, permanent load GK 1.0 kilonewton, variable load QK 3 kilonewton meter square, and this value is we can find on the question. Design life 50 years, this can find on the table 2.1 EN 1990. And fire resistance is R60 because on the question they have said that the slab is outside building which subjected to 1 hour fire resistance. So this means the fire resistance is R60, 60 minutes. Exposure classes XC3. Material strength, characteristic strength of concrete FCK 30 Newton millimeter square. Characteristic strength of steel FYK 500 Newton millimeter. Unit weight of reinforced concrete 25 kilonewton meter. And also assume the diameter of bar is 12 mm. So for step 1 and step 2, first is settle. Step 3 and step 4. For step 3, determine thickness of slab. So minimum thickness for fire resistant is 80 mm. Estimate thickness considering deflection control. H equals to 4250 over 26, and we get the value 163 mm. So from the table 5.8, we get the value of H is 175 because it's close to 163 mm. So step 4, calculate minimum cover for durability, fire and bond requirement. So C min B equals to 12 mm, C min dur equals to 20 mm, and minimum required exit distance for R60 fire resistant is A equals to 20 mm from table 5.8, and minimum cover with regard to fire C minimum equals to A minus diameter bar over 2 minus and equals to 20 minus 0.5 12 and equals to 14 mm. And next, allowance in design for deviation, C deviation equals to 10 mm. And last, we calculate the nominal cover, C norm equals to C min plus C deviation. So from the value that we get before, we just insert 20 plus 10 equals to 30 mm. So we use the value of C norm is 30 mm. Step 5 and step 6, we combine it in one-way calculation. For slab safe weight 0.175 times 25. 0.175 is from the slab thickness H, and 25 is unit weight of concrete. So the answer is 4.38 kilonewton meter square. Permanent load excluding safe weight is 1.0 kilonewton meter square. So the value of 4 and 1 we plus, and we get 5.38 kilonewton meter square for characteristic permanent action GK. And next, characteristic variable action QK equals to 3 kilonewton meter square. And we calculate design action, ND equals to 1.35 GK plus 1.5 QK. And the value we get is 11.676 kilonewton meter square. And we consider that 1 meter width WD equals to ND times 1, and we get 11.76 kilonewton per meter. So next is we calculate the critical and shear force, the critical moment and shear force moment. So for shear force, V equals to WD L per 2, and we get the answer is 25.0 kilonewton meter. And for bending moment, M equals to WD L square over 8, and we get the critical moment is 26.5 kilonewton meter. Next is step 7, that is main reinforcement. Now we calculate the value of effective depth. D equals to H minus C nominal minus 0.5 diameter bar. So we get the answer is 139 mm. After that, design moment MED that we calculate from the calculate before, that is 26.5 kilonewton meter. So now we calculate the value of K, where K is equals to M over BD square FCK. So we get the value of K is 0.046, that is less than K bar 0.176. So that means that compression reinforcement is not required. Now we calculate for tension reinforcement. Z equals to D in bracket 0.5 plus square root 0.25 minus k over 1.134. So we get the value is 0.96d, which is less than 0.95d. So now we calculate the AS. AS equals to m over 0.87 FYKZ, and we get the value is 462 millimeter square per meter. Next, we calculate minimum and maximum reinforcement area. So AS min equals to 0.26 FCTM over FYK times BD. So from the formula, we get that 0.0015 BD, and we just insert the value 0.015 times 1000 times 139 mm, and we get the answer is 209 millimeter square per m. And for AS max is equals to 0.04 AC and equals to 0.04 times 1000 times 175. So the value is 7000 millimeter square per m. So we get that main bar is use H12. Why we use H12? Because from the first specification we assume that diameter bar is 12, so we use it H12. H12 225, that is 503 millimeter square per meter. And secondary bar we use H12 450, that is 251 millimeter square per meter. Next is step 8, that is check shear. So design shear force VED equals to 25 kilonewton. So design shear resistance VRDC is use the formula that given, and the value of K is 2.20 is less than 2. Value of P1 equals to 0.036, which is less than 0.02. VRDC equals to 73.9 kilonewton, and V min is equals to 75.4 kilonewton. So VRDC 75.4 kilonewton is more than VED 25 kilonewton, so its check is okay. So step 9 is check deflection. For the value of percentage required tension reinforcement, P equals to 0.0033, and difference reinforcement ratio PO equals to 0.0055, and factor for structural system from table 7.4N, K equals to 1.0, and P is less than PO, so we must use the equation 1, which is equation LD, and the equation is like this, and we get the value of L over D is 33.7. Modification factor for span less than 7 meter is 1. Modification factor for steel area provided is equals to 1.09, which less than 1.5. So from the value that we get, LD allowable equals to 36.63 and LD actual is equals to 30.6. So LD actual is less than LD allowable, so the check for deflection is okay. And the second last step is check cracking. For cracking, the value is H is 175, main bar, S max slab is 400 mm, max bar spacing is 225 mm, which is less than S max slab, so the cracking is okay. For secondary bar, S max is 450 mm, so max bar spacing is 450 mm, is less than S max slab, so the cracking is okay. So the last step is detailing drawing. So this is the detailed drawing for the question and for the slab. So dimension span equals to 4,250 millimeter. That is from the question. Thickness H 175 millimeter. That what we calculate from the slab thickness. Concrete cover 30 millimeter. And for reinforcement 1 is H12 225 spacing. and for reinforcement 2 H12 spacing 450 mm.
Design of beam. A beam is a load-bearing element that typically spans between columns or walls. It can carry vertical loads such as the weight of floors, walls, and other elements, and transfer them to the supporting columns or wall. Types of beam. Simply supported beam. This type of beam is supported at both ends, usually by columns or walls, and is free to rotate at two supports. Cantilever beam. A cantilever beam is anchored at one end and extend freely beyond its support. Continuous beam. Continuous beam have multiple supports along their length, allowing them to distribute load more evenly. Example of beam: simply supported beam and continuous beam. Example: Step 1. Determine design life. Step 2. Determine preliminary size of beam. Step 3. Estimate actions on beam. Step 4. Assess durability requirements and determine concrete strength. Step 5. Determine nominal cover for durability, fire, and bond requirements. Step 6. Analysis structure to obtain critical moment and shear force. Step 7. Design of flexural reinforcement. Step 8. Design shear reinforcement. Step 9. Verify deflection. Step 10. Verify cracking. And Step 11. Produce detailed drawings.
Next is continuous beam. Continuous beam are one that rests on more than two supports and a common element in situ construction. Typical failure mode, bending moment, and main reinforcement of a construction beam.
This is example question for continuous beam. Step 1. Specification. This is our design continuous beam. Next is dimension. Span L equal 8.00 m, width B equal 3.00 m, slab thickness equal 110 mm, beam size equal 225 times 500 mm, characteristic load finish equal 1.5 kN per meter square, variable QK equal 3.0 kN per meter square, materials unit weight of concrete equal to 5 kN per meter cube, characteristic strength of concrete equal to 5 N per mm square, characteristic strength of steel equal 500 M per mm square, characteristic strength of link equal 500 N per meter mm square, nominal concrete cover equal 30 mm, assume bar 1 equal to 0 mm, bar 2 equal 16 mm, bar link equal 6 mm. Okay, next is effective flank width. BW equal 2 to 5 mm, HF equal 110 mm, H equal 500 mm, B1 equal 1400 mm, B2 equal 1400 mm, actual flank width B equal B1 plus B2 plus BW equal 30 to 5 mm. Effective flank width BF equal BFI plus BW more than B. BF I equal 0.2 BI plus 0.1 LO more than 0.2 LO. Next span AB CD. LO equal 0.85 L equal 0.85 times X000 equal 6800 mm. B if I equal 960 mm more than 1360 mm. Use 960 mm. BF2 equal 960 mm more than 1360 mm. Use 960 mm. BF equals 960 plus 960 plus 225 equal 2145 mm more than 3025 mm equal to 145 mm. Span BC IO equal 0.7 L equal 0.70 times x000 equal 5600 mm. BF1 equal 560 mm more than 1120 mm. Use 560 mm. BF2 equal 560 mm more than 1120 mm. Use 560 mm. BF equal 560 plus 560 plus 225 equal 1345 mm more than 3025 mm equal 1345 mm.
Action on beam 1A AD. Distribution of action from slab panel 1A over AD. Ly over Lx is 2.7, which is one-way slab, and the shear coefficient is 0.5. For panel 1A to AD, Ly over Lx is 2.7, also one-way slab, and the shear coefficient is also 0.5. For characteristic permanent action, Gk equals to 14.94 kN per meter, and characteristic variable action Qk is 9.0 kN per meter. For design load is 33.67 kN per meter. Main reaction span AB and CD. The effective depth is 454 mm. Bending moment is 1334 kN/meter, which is M smaller than MF. Neutral exists within the flange. K equals to M over FCK BD square, so the answer is 0.018. Z equals to D times 0.5 plus square root 0.25 minus K over 1.134 equals to 0.98D. As area of tension reinforcement, AS equals to 1034 mm square. For minimum and maximum reinforcement area, AS min is 136 mm square. For AS max is 4500 mm square. For support B and C, the effective depth is 444 mm. The bending moment is 237 kN/meter. For the K is 0.214. The distribution is 0%, and the distribution ratio is 1.0. So the K ball is 0.167. For step 4, K is larger than K ball. D1 equals to 44 mm. So the answer for Z is 364.4 mm. For X is 199 mm. D1 over X is 0.22, which is smaller than 0.38. The compression steel will have yielded FSC equals to 0.87 FYK. Area of compression steel AS1 is 299 mm square. Area of tension steel AS is 1466 mm square. For AS min is 136 mm square. For AS max is 4500 mm square. Span BC. Effective depth D is 444. For bending moment, M is 151 kilonewton meter. So after the calculation, we got the Z, D times 0.5 plus square root 0.25 minus K over 1.134 equals to 0.98D. And then for shear reinforcement concrete strut capacity, VRD max equal to 0.36 BW Dcc50203 times 1 minus FCK over 250 over cot theta plus tan theta. So the answer is theta equals to 22 degree, cot theta 2.5. Theta equals to 45 degree, cot theta equals to 1.0. For support A and D, VED is smaller than VRD max cot theta 2.5 and also smaller than VRD max cot theta 1.0. Therefore, angle theta is smaller than 22 degree. As for shearing, ASW over S is 0.277. So trailing H6 ASW equals to 57 mm square. As for spacing, 204 mm smaller than 0.75D equals to 341 mm. Additional longitudinal reinforcement. Additional tensile force FTD equals to 150 kilonewton. For MED max over Z is 450 kilonewton, bigger than FTD. For AS rec is 345 mm square. Step 6. Support B and C. VED equal to 162 kilonewton. Therefore, smaller than VRD max cot theta 2.5 and also smaller than VRD max cot theta 1.0. Therefore, angle theta is smaller than 22 degree. For shearing, ASW over S is 0.369. So, trailing H6 ASW equals to 57 mm square. For spacing, S is 341 mm. Additional longitudinal reinforcement, additional tensile force FTD equals to 200 kilonewton. AS rec is 460 mm square. For shearing, ASW over S is 0.338. So trailing H6 ASW equals to 57 mm square. For spacing, S is 167 mm smaller than 0.75D equals to 341 mm. For additional tensile force, FTD equals to 183 kilonewton. For AS rec is 422 mm square. And then for step 7, deflection. Check at span AB. Rho equals to AS rec over BD equals to 0.01. For reference reinforcement ratio, rho 0 equals to 0.005. And then factor for structural system, K equals to 1.3. So the answer is 19.1. And then factor for structural system, K equals to 1.3. So the answer is 19.1. Modification factor for flange width is 0.8. Modification factor for span greater than 7 meter is 0.88. After that, modification factor for steel area provided is 1.52, larger than 1.5. Therefore, allowable span effective depth ratio is 20.1 and for actual is 17.6, which is smaller than the allowable span. And then cracking, limiting crack width is 0.3 mm. For steel stress is 262 Newton over millimeter square. For maximum allowable bar spacing is 150 mm. Bar spacing S equals to 66.5 mm smaller than 150 mm. And then this is the detailing picture of our calculation.
What is column? A column is a structural element which subjected to axial compressive force. Column is a structure carry the loads from the beams and slab down to the foundation. Although primarily carry axial load, column may also have to resist bending moment due to continuity of the structure and eccentricity of loading. Column can be classified into two types. Firstly is braced and unbraced column. A column may be considered to be braced in a given plane if lateral stability of the structure as a whole is provided by walls or bracing, designed to resist all lateral force in that plane. Otherwise, the column should be considered as unbraced where the lateral loads are resisted by the bending action of the column. The second type of column is slender and non-slender column. Column may be classified into slender or non-slender depending on its sensitivity to second order effect. Column can be deemed to be non-slender when design actions are not significantly affected by their deformation. Second order effect may be ignored provided the slenderness ratio of the column does not exceed a particularly limiting value. Effect also can be ignored if the less than 10% of the corresponding first order bending moment. Slenderness ratio provides a measure vulnerability to failure of the column by elastic instability or buckling. Short column with low slenderness ratio invariably fail under ultimate loads with the material reaching its ultimate strength and not by buckling. On the other, slender columns with very high slenderness ratio are in danger of buckling under relatively low compressive loads. Example for calculation of column. Determination of non-slender or slender column. The first step is we must determine the specification given. From the picture, we were shown that the column height is 5000 mm. The size for first main beam is 250 x 500 with the length of 6000 mm. The second main beam size is 250 x 600 with the length of 8000 mm. For the first secondary beam, the size is 250 x 400 with the length of 4000 mm, same as the secondary beam 250 x 400 with the length of 4000 mm. The material that we use is FCK 25 Newton mm square, FYK 500 Newton mm square. The moment and axial force is 250 and 350 mm. For the NED was given is 1050 kN, which MZ 55 kNm and negative 6 kNm. For the MY is 15 kNm and negative 10 kNm. For the second steps is determine the dimension and size. For column, the size is 275 x 350 mm, and we get the length for IZ is 5000 minus 500 equal to 4500 mm square mm. For IY 5000 minus 400 and we get 4600 mm. For the beam size for the main beam is 250 x 500 and the length is 6000 mm. For the second main beam is the length is 8000 mm. For the secondary beam, the size is 250 x 400 mm, which the two of the beam length is equal, which is 4000 mm. For moment of inertia is I equal to BH3 power of 12 divided by 12. Column IZZ, we get 275 x 350 power of 3 divided by 12, which equal to 0.98 times 10 power of 9 mm4. For IYY, 350 x 275 power of 3 divided by 12, we get 0.61 times 10 power of 9 mm4. For the beam, main beam size is 250 x 500 power of 3 divided by 12, we get 2.60 times 0 power of 9. Secondary beam, 250 x 400 power of 3 divided by 12, we get 1.33 times 10 power of 9 mm4. The next step is determination of stiffness. K equal to EI divided by I. For column KZZ, 0.98 times 10 power of 9 divided by 4500, we get 2.18 times 10 power of 5. For KYY, 0.61 times 10 power of 9 divided by 4600, and we get 1.32 times 10 power of 5. For beam main KMBL, we get 2.60 times 10 power of 9 divided by 6000, and we get 4.34 times 10 power of 5. For KMB2, 2.60 times 10 power of 9 divided by 8000, we get 3.26 times 10 power of 5. For the secondary beam, we get 1.33 times 10 power of 9 divided by 4000, and we get 3.33 times 10 power of 5. For relative column stiffness, z-axis top and K2, we get 2.18 divided by 2 times 4.34 plus 3.26, we get 0.14, much bigger than 0.1, so we use 0.14. For both and K1, 2.18 divided by 2 times 4.34 plus 3.26, we get 0.14, also much bigger than 0.1, so we use 0.14. For y-axis top and K2, we get 1.32 divided by 2 plus 2 times 3.3 plus 3.3, we get 0.10, so we use 0.10. For both and K1, 1.32 divided by 2 times 3.3 plus 3.3, we get 0.10, so we use 0.10. The next step is determine the effective length of column with the reference of 5.8.3.2. So the formula is I OZ equal to 10.5 IX open bracket 1.24 times 1.24 close bracket power 1 over 2, and we get 0.621 LZ, and we get 0.621 times 5500, and we get 2795 mm. For I or Y, we get 0.5 LY open bracket 1.18 times 1.18 close bracket power 1 over 2, and we get 0.59 LY, which equal to 0.591 times 4600, and we get 2718 mm. For the radius gyration, I equal to I over A times 1 over 2, and we get IZ 0.98 times 10 power of 9 divided by 96,250 power 1 over 2, and we get 101.0 mm. For IY, we get 0.61 times 10 power over 9 times 10 power of 9 divided by 69,250 power 1 over 2, and we get 79.4 mm. For slenderness ratio, I equal to IJY with the reference of 5.8.3.21, we get lambda 2795 over 101, we get 27.7. For lambda Y, we get 2718 over 79.4, and we get 34.2. Next is determine of slenderness limit with the reference of 5.8.3.1. For the formula is 20 times A times B times C over N power 1 over 2. So A, we get 1 times 1 divided by 1 plus 0.2, we get 0.7. For B, 1 plus 2W power of 1 over 2, we get 1.1. For C, 1.7 minus Rm, where Rm equal to MOL divided by MOZ. So for z-axis, Rm we get negative 6 divided by 55, we get negative 1.11. For Cz is 1.70 minus negative 1.109, we get 1.59. For y-axis, we get Rm is negative 10 divided by 15, and we get negative 0.67, and we get Cy 1.70 minus negative 0.667, and you get 1.03. For n equal to NED divided by AFCD, where AC equal to 275 times 350, and we get 0.96 times 0 times 10 power of 5 mm. For FCD equal to 0.85 FCK divided by lambda C. So 0.885 times 25 divided by 1.5 equal to 14.17 N per mm square. For N is N equal to 1050 times 10 power of 3 divided by 0.96 times 10 power of 5 times 14.717 equal to 0.77. For z-axis limit, 20 times 0.7 times 1.1 times 1.59 divided by 0.77 power 1 over 2, we get 27.9, which more bigger than lambda z is 27.7, and column is non-slender for about z-axis. For y-axis, L lim is 20 times 0.7 times 1.1 times 1.03 divided by 0.77 power of 1 over 2, and we get 18.1, much smaller than lambda y, which is 34.2, and it's shown that column is slender about y-axis. The last step is determine the effective length of column using simplified method by the reference of table 10.1 module. So the effective length LO equal to factor times clear height. For x-axis, n condition top equal to 1, both equal to 1, factor equal to 0.75, and we get LOZ equal to 0.75 times 4,500, and we get 3,375 mm. For beam at both sides, H beam must bigger than H column. 600 is bigger than 350. For y-axis, n condition top equal to 1, both equal to 1, factor is also the same, 0.75, and we get LOZ equal to 0.75 times 4,600, and we get 3,450 mm, and beam at both sides also, H beam is bigger than H column, which is 500 bigger than 275. For slenderness ratio, lambda equal to LJY, which is lambda z 3,375 divided by 101.0, and we get 33.4, which is bigger than lambda lim z, which is 27.9, which is column is slender about z-axis. For lambda y is equal to 3,450 divided by 79.4, which is 43.5, is bigger than lambda lim y, which is 18.1. So column is slender for about y-axis also.
So in conclusion, reinforced concrete has been proven to be one of the most versatile and innovative building materials over the past century. Its unique synergistic properties provide the strength, longevity, formability, and fire resistance needed for all types of modern structures.